Good day, students. Welcome to math.circ.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 11 to 15 of the Algebra 1 January 2016 New York Regents exam. So the goal here is to really cover the problems in depth so that you are able to do well and understand the problems on the upcoming Regents exam. If you have any questions on the problems you're working on, just place it in the comment section below. I'll be glad to assist you. If you just want the worked out solutions, go ahead and click on this link right here for the worked out solutions. All right, let's take a look at problem 11. It says Joe has a rectangular patio that measures 10 feet by 12 feet. He wants to increase the area by 50% and plans to increase each dimension by equal lengths W. Which equation could be used to determine X? Now, one tip you want to keep in mind concerning percent increase is that if you want to increase a certain measure by, let's say, R%, you can simply multiply that measure by 1 plus R over 100. Before we get started with the solution to the problem, let's go ahead and write down two formulas that we're going to be using for this problem solving process, okay? So formulas. The first one has to do with percent increase, okay? Formula number 1, percent increase. So in order to get the final value, so the final is basically going to be the initial value multiplied by 1 plus R divided by 100, okay? This is percent increase by R%. The second formula we're going to be using in this problem is your simple area formula. The area of a rectangle is given by length times width, okay? Now in this problem, we're dealing with a geometric figure, namely a rectangle, and alterations have been made to the measures of the sides or the dimensions. So one really good strategy to use when setting up algebraic equations involving geometric figures is to give yourself a visual, okay? So we're going to go ahead and draw a rectangle with the original dimensions, and then we will give ourselves a visual as to what the increase in the dimensions look like, okay? So this is not drawn to scale by any means. So let's say this is the original rectangle, okay? The original patio. So the original patio is indicated in the problem is 10 by 12. So 12 by, let's change the color here, 12 by 10. Okay, now what happened is that Joe increased the length and the width by x, okay? So this is the formal width and this is the formal length. So they increased each measure by x, okay? So this one was increased by x units. Let's see, that's x. And the other was also increased by x units, okay? So we just add 3 boxes right here. So that's basically what the increment looks like. All right. So this right here is x, and let me change the color of that. This is x, and that is x. So can you visualize what the new rectangle is going to look like? Let's go ahead and sketch what the new rectangle looks like. So it's going to look like that, much bigger. Okay. So this new rectangle has an area that's 50% more than the original area. All right, so let's go ahead and label the dimensions of our new rectangle while we're at it, so it can assist us in setting up our equations later on. Okay, so this is our new length. All right, so let's write that down. Our new length is going to be 10 plus x. From here to here is 10. See, from here to here is 10, and then we're just adding x on the top, okay? So our new length is going to be 10 plus x. Can you tell what our new width is going to be? Our new width is going to be 12 plus what? 12 plus x. Okay, so our new width is 12 plus x because we're combining this portion right here, which is 12, and then the x portion right there. So 12 plus x is our new width. Okay, so now let's go ahead and set up our equations. Okay, so let's write down an equation. So we have a 50% increase in area okay, is going to be equal to the increase in length plus, I'm sorry, so area is length times width, okay? So 50% increase in area is going to be increase in length times the increased width. Okay, so the word I was looking for is actually increased length times increased width. Okay, how do we know this? We know this because of the formula for the area of a rectangle. Let's put that back up. Area of a rectangle is length times width. Okay, so the new area, which is 50% increase over the old one, is going to be the increased length times the increased width. Okay, so let's indicate what these components are. So our increased length is what? Our increased length is 10 plus x. Okay, and then our increased width is what? 12 plus x. Okay, so these are the two dimensions that we're going to be multiplying to get the 50% increase in area. So what on earth is a 50% increase in area? Well, let's go ahead and calculate it. 50% increase in area is going to be the original area. The original area, what was the original area? The original area, let's say A original, is going to be length times width, is 10 times 12. Okay, so what we're going to do is we're going to take that original area and multiply it by the adjustment factor. Okay, so let's write down what we're looking for here. Original area times 1 plus the percent increase in decimal form, or we could write it as a fraction as we indicated earlier, 1 plus 5 over 100. Okay, 1 plus 5 over 50 over 100. So 50 is a percent increase, divide that by 100. All right, so that is how we will calculate our 50% increase. Okay, so our original area, let's do it over here. Original area is 10 times 12, which is 120. Okay, so 50% increase is going to be the original 120 times 1 plus 50 over 100 is 1/2 or just 0.5. Okay, and when you plug this into your calculator, you will end up with 180. Or you can even do this mentally. If you think about 120, what is 50% of 120? 50% of 120 is 60. If you add 60 to 120, what do you get? 180. Okay, now we have what we're going to be using. We're going to use this equation, this expression and this value. We're going to substitute it here, and we'll have the setup that can help us to solve for x. That results in a 50% increase in the area. Okay, so 50% increase in the area is 180. We just calculated that. The increased length is 10 plus x. Okay, times the increased width, which is 12 plus x. Okay, And as you can see, our correct answer is option number 2. Option number 2 is the correct answer for this problem. Okay, let's take a look at problem 12. We have a cubic trinomial that we are asked to factor. So we are to factor x to the third minus 13x squared minus 30x. We're factoring it completely, okay? Complete factorization. Now, if you look at all the options, what do you notice? You notice that an x has been factored out. So that clearly indicates that x should be a common factor of every single term in this cubic trinomial. And it definitely is. So since we have that x as a common factor, we have to factor it out. When you factor out a variable, it's as though you're dividing by the variable that you factored out, okay? So if I take x to the third and factor out x, what do I have left? I have x squared, okay? And then minus 13x squared, if I factor out an x from x squared, I'm left with 13x. And then if I take out x from 30, I'm left from 30x, I'm left with 30, okay? Now let's go ahead and factor out this trinomial. Now this is a very tricky problem, and you want to proceed with caution. Why is that the case? Check this out. When you multiply 3 times 10, what do you get? 30. When you multiply 2 by 15, what do you get? 30. So you have two potential candidates that could work here, but you have to let the signs be your guide, okay? Anytime you have factorization problems like this, where two possible pair of numbers could work, you want to proceed with extreme caution, okay? All right, so I'm going to factor this using the x game. AC goes on top, B goes on the bottom. A is 1, A times C is negative 30, and B is negative 13, okay? Now this is where we want to exercise caution. We want to ask ourselves, what two numbers multiply to give us negative 30 and add to give us negative 13, okay? So 30 is a product. We have 1 times 30. This doesn't work because if you combine it, you get 31 or 29. That's no good. 2 times 15. 2 times 15 kind of sort of works because when you multiply, you get 30, and it's linear. Adding it, you can get 15, 13, 3, 10, 5 times 6. I think we've exhausted all the combinations, okay? So what makes this problem tricky, as indicated earlier, is that these two numbers look like they could work. But how do we know the exact combination? So we have to let the signs be our guide, okay? Now, let me try 2 and 5. I'm sorry, 2 and 15. Let's see if it works, okay? So the product has to be negative. So if the product is negative, then one of them must be negative. Okay, so if 15 is negative, 2 minus 15 is negative 13, and 2 times negative 15 is negative 30. Well, that works. Perfect. So just make sure that this works before you insert it, okay? So we're going to go ahead and go x times x plus 2 times x minus 15. Okay, so we can clearly see that our answer is option number 3. All right, let's take a look at question 13. It reads, the table below shows the cost of mailing a postcard in different years. During which time interval did the cost increase at the greatest average rate? So one thing you want to note is that average rate over an interval is basically the same thing as a slope of the line through those points, okay? So when you see the word average rate, there's no need to panic. It's something you've done before. It's the same thing as the slope of a line through those points in the interval under consideration, okay? So let's start off by writing down the formula that we're going to be using for this problem. So the average rate, I'm trying to keep the notation easy for you so you can remember how to do it on the day of the Regents exam. So the average rate is simply y2 minus y1 over x2 minus x1. Okay? Now, in the context of this problem, what is x and what is y? We want to keep our variables short and sweet. We don't need too many variables all over the place or else we'll get confused. Okay? So the independent variable is the x and the dependent is the y. Okay? So x is the independent, the year, time is independent, and the cost is dependent on the independent variable. Okay, so these are my x's and these are my y's. All right, over the intervals, I will be computing the change in y over the change in x. Okay, so I'm going to be giving a visual as to what my y2 minus y1 and x2 minus x1s are. All right, so this will be up here, I'll be doing my change in x's, and down here, I'll be doing my change in y's, okay? All right, now we have 5 values, so we're gonna have 4 changes happening. So first one is from 1898 to 1971. Okay, so if you change this right here is a change in x2 minus x1, and then this would be my change in y. So let's call this interval 1. And then for interval 2 will be from 1971 to 1985, and the cost is x2 minus x1, 14 minus 6. This is interval 2. And then interval 3 is 1985 to 2006, change in x over change in y. And then we have one more, 2006 to 2012, change in x over change in y. Okay, so this is 4, and this is 3. All right, I'm just going to be calculating the average rate on these intervals, and then the one that's the greatest will be our answer, okay? So let's calculate the average rate for interval 1, okay? So it's going to be change in y, 6 minus 1 divided by change in x, which is x2, remember the second one comes first, minus the first one, 1898. All right, so we can just plug this into our calculators to compute the quotient. Okay, so now when you're entering the quotient like this, you want to make sure you make use of parentheses so that you do not have grouping errors in your computation. So 6 minus 1 divided by 1971 minus 1898. Oh, I left out my parentheses. Let's insert that. So in the numerator and especially the denominator, make sure you use parentheses so you don't have a grouping error. Okay, so there goes my first ratio, 0.0684. So 0.06884, well, we can just round it to 5. All right, so let's go ahead and do the next one. We're going to compute the average rate of change on interval 2. So average rate on interval 2 will be y2 minus y1 divided by x2 1985 minus x1 1971. Okay, let me just set them all up so I don't keep going back and forth, all right? So average rate for interval 3 is going to be y2 minus y1, the one on the left minus the one on the right, the one on the right minus the one on the left, x2 minus x1. Okay, I'll calculate it in a second. And then lastly, we have the average rate over interval 4, 2006 to 2012, y2 minus y1 divided by x2 2012 minus x1 2006. Okay, now I'm just going to enter all of them in the calculator real quick, and we're looking for the biggest one. So let's see what we have here. So for interval 2, parenthesis 14 minus 6 divided by 1985 minus 1971. All right, let's take a look at what we just entered, make sure it's correct. So 14 minus 6 divided by 1985 minus 1971. Enter. Oh, wow, that's bigger. Okay, let me write it down. So for this one, I have 0.5714. 0.5714. Moving along, remember we're looking for the greatest, so we have to do every single one of them, okay? 24 minus 14 divided by 2006 minus 1985. All right, let me check to make sure I entered it correctly. 24 minus 14, 2006 minus 1985. Average rate, 0.4762. 0.4762. Okay, let's check the last interval. What's happening here is interval number 2 is leading right now. It's the biggest one. 24 minus, oh, already did that. Oops, I took away all my work. That's okay. All right, and then the last one we have 35 minus 24 divided by 2012 minus 2006. Bam. Oh, we have a winner. This is the biggest one, 1.83 repeating. So let's write that down. 1.833 repeating. Okay, so we can clearly see that on this interval, interval 4, from 2006 to 2012, that's where we had the greatest average rate. Okay, so answer is option number 4. All right, let's take a look at question number 14. It reads, when solving the equation x squared minus 8x minus 7 equals 0 by completing the square, which equation is a step in the process? So one thing you want to note when completing the square is that if you're dealing with a quadratic equation, in order to preserve equality, whatever you add to one side of the equation, you must add the same value to the other side, okay, so that you preserve equality. Let's take a look at the formula for completing the square, and that should give us a visual as to what I'm talking about. So let's say you have an incomplete square, x squared plus bx, and you were to add a number to make it a perfect square trinomial, but you had already moved c to the other side. You also have to add the same number. Okay, so what do you add to both sides to make a perfect square trinomial? To complete the square, you add b over 2 square. Okay, if it's in this format, so I'm going to add b over 2 square. Guess what? By inserting b over 2 square in the setup on the left, I have a perfect square trinomial. Okay, so to preserve equality, this new term I introduced on the right, I have to introduce exactly the same term on the right. Okay, I get my left and right mixed sometimes. So what I introduce on the left side, I have to introduce on the right. Okay, so this is something you want to keep in mind. All right, now, and another thing you want to keep in mind is when you're factoring, you want to take the square root of the first and the last term. The middle term, all it just contributes is a sign, and that tells us the factored state, which would be x plus b over 2 quantity square. All right, you do not want to take the square root of the b. That's incorrect, or even extract b. Okay, so let's keep that in mind. We're going to apply these points to this quadratic equation. X squared minus 8x minus 7 equals 0. So the question asks for which equation is a step in the process. We don't have to solve it. We just want to keep working through the steps until we get to a form consistent with these options, namely a factored perfect square. Okay, this is a factored step. The next step is the square root property, and then you isolate your x. we don't have to do that here, okay? Now, first step is to create an incomplete square on the left side. So to accomplish that, I'll toss the C term to the right, add 7 to both sides. I don't know if it creates a perfect square trinomial. I'm just going to toss it over there and see what happens, okay? Now, if it's moved over to the other side, is equal to 7. Now, I'm going to, I have to add a term to this side right here that makes it a perfect square trinomial, okay? But guess what? Whatever I add to this side, I have to add exactly the same value to the right side in order to preserve equality. So what is that number that makes this a perfect square trinomial? Well, we have to extract what B is. A is 1, B is 8. Okay, so B equals 8. What are we going to do with that? Remember the formula? B over 2 squared. So divided by 2, okay? And then you square that, you get 16. So by adding 16, here I have a perfect square trinomial. But what do I want to remember to do? I have to add a 16 here also. Okay, so this now becomes, oh, now I can factor this because I have a perfect square trinomial. Now, one mistake students make is they just take x and 8, group it together and square it. That's wrong, okay? What you want to do is you square root the first and the last term. If you don't like to use this method, you can use the factorization algorithm to still accomplish the same results. The middle term, we're just going to extract the sign. All right, so it's now going to be square root of x, where is x, minus square root of 16, 4, quantity square, equals 7 plus 16 is 23. Okay, so our answer is option number 2. That's the answer for number 14, so let's write that down. Option 2. Okay, let's take a look at question number 15, the last in this review installment. It says a construction company uses the function f of p, where p is the number of people working on a project, to model the amount of money it spends to complete a project. A reasonable domain for this function would be. Now, one reminder concerning the domain of a function is that for a function f of x, x is the input and the domain of f of x are the constraints on the inputs. Okay, a function has two parts, input and output. Domain has to do with the inputs. All right, let's do a real quick anatomy of functions. Just to illustrate what I'm talking about. So what are the meaning of the different components of a function? So let's say we have a function f of f of x equals y. Okay. Now check this out. This y right here, y is known as the output. Okay, this is the output. And the constraints on the output is the domain. So constraints is the domain. I'm sorry, constraint is range. So the constraint on the output is known as the range. Okay, how big can the output go? How low can the output go is the range. Okay, think about it as the vertical span of the graph of this related function. So the constraint on the output is the range. Now this little variable right here, what is in the parentheses, that is your input, is also known as your independent variable. The output is dependent on what? On your inputs. Okay, it's just like a soda machine. If you put in money, you get your soda. So the output is soda, your input is the dollars that you put in there. Okay, so this is independent. Now the constraint on your input, so let's say you go to a soda machine and you put in pieces of paper in there, it's not going to work, right? You have to put in dollars. So the constraint or the acceptable input is the domain. Okay? All right, so let's keep that in mind for this problem that we're working on. So we're given a function f of p. Okay, f of p, the output f is the amount of money. Okay, amount of money. This is the output. Okay, but p, what's going into the function is the number of people. Okay, p is a number of people. Now, this is a question. Which is the domain and which has to do with range? The output is the range, okay? The constraint on the output is the range. The constraint on the input is your domain. All right, so in this problem, we're looking at what are the constraints, what is reasonable when you're determining the number of people to accomplish a certain task. Okay, so we're looking at P, the number of people. These are the options we have here: positive integers, positive real numbers, both positive and negative integers, both positive and negative real numbers. We can do some elimination here. Does it make sense to have negative people? We're not talking about attitude, we're talking about numbers, okay? We know there are negative people out there, but can you have negative number of people working? It doesn't make any sense, right? So since you cannot have negative number of people, then we can eliminate option 3 and 4, all right? So the question is, which of these group set of numbers is reasonable for representing number of people? Integers or real numbers? That's the question. Okay, so to determine what the correct answer is, the best option, the reasonable option, let's do a real quick review on what integers and real numbers are, okay? And then we'll see which of them makes sense. So what are integers? Well, integers, let's consider some examples or numbers such as 0, 1, 2. Oh, since we're looking for positive, we gotta be careful here. Positive integers. Okay, positive integers 0, 1, 2, 3, 5, da da da. Basically whole numbers. Okay, whole numbers. That's what positive integers are. How about positive reals? What are positive real numbers? Positive real numbers are 0 is a real number, by all means. 1 is a real number. 1/2 is a real number. Root 3 is a real number. 0.572 dot 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 is a real number. 0.6 repeating is a real number. So basically, real numbers are integers. Okay, we're looking at whole numbers, radicals, fractions, and all decimals. It doesn't matter if the decimal is terminating or repeating. They are all reals. Okay? So now let's take a look at these two sets of numbers. Which of these is reasonable for representing the number of people? Does it make sense to have half a person working on a project? Makes no sense, right? But integers are a reasonable domain or set of numbers for representing the number of people. Okay, so our answer, oh, sorry about that. So our answer is positive integers. Okay, positive integers is the correct answer. Let's see what. So option number 1 is the answer for number 15. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to subscribe so you can get updates to the remainder of this review series. As you're preparing for your upcoming exam, if you have any questions that you would like assistance with, just place your comments in the comment section below. and we'll be glad to assist you at your earliest convenience. More clips can be found on mathwithserve.com under test prep. Thanks again for watching and have a wonderful day.